Hello, everyone. Got a couple minutes. I'm waiting for more people to show up. I'm checking a row while I'm waiting for more people to show up. I'm going to pause this while I do the row. I start recording back up and find my image of myself. There I am. Okay. So does anybody have any questions on stuff we've covered so far? How did the test go? Everybody feel okay about it? Anything seem horrible? Find any boo-boos or anything like that?
Do we have until midnight to do that, right?
I might have set it till midnight. I can't remember if it's midnight or 9:30 this morning. I'll check it for you real quick though.
Okay.
Hold on just a second and let me look at that. Modules. Yes, tonight at midnight.
Okay, thank you.
No problem. All right. Anybody have any question? I guess we can't ask any specific questions since the test is still out, but if you could generalize it or something, I certainly can help you with that. But I suspect people that have already taken one attempt probably have a pretty good feel for what's going on with it.
I had a question about the homework.
What's that now?
I said I had a question about the homework.
Go for it. Yeah, that'd be great.
So on Canvas, it says that the part 2 is due today, but then on Mastering, it says part 2 is due the 27th for chapter 25.
Yeah, I set some dates back. You can always trust the dates on the mastering side.
Okay.
Because sometimes I'll make changes in my plans and just give you all a little bit more time. So yeah, and plus if it's later, it's my fault. So it's something I got to deal with, not you. Just remember everything has to be done by, I think August 14th is our last day of class. So I usually make sure everything's done before noon on August 14th or even before midnight the day before.
And also there was a lot of ray drawing problems for part 1, and I did not understand how to do that with Mastering at all. I was very confused.
Yeah, you might want to go back and do one of those introduction things. That'll help you a little bit, but that might be something I can address a little bit during lab. Maybe I'll pull it up and figure it out with you. It's been probably 2 years since I played with the ray diagrams and mastering. I just knew it would be good practice for you, so I gave it to you guys. But yeah, I'm sure the problem you're having isn't knowing what rays to draw, but rather how to draw them in mastering.
Yeah, because I can do it on paper with a ruler and stuff, but doing it online is very difficult.
Yeah, let me let me see what I can do. We probably can fit something like that in lab. Actually, lecture's going to be pretty short today. We're going over special relativity, which is, if you look behind me, most of my physics, I did my PhD work in relativity, actually in the general theory of relativity, which is the one that covers gravity. So I love this stuff. And the parts that we've traditionally covered are fairly straightforward. So we should be able to finish that rather quickly. Anything else, anyone?
I had a question about the syllabus.
Yes.
Just because like in the calendar where it has like the Monday, Wednesday, Friday, and it shows us everything,
Mm-hmm.
I'm just confused because there's only like 3 online tests and then the midterm and final, but underneath it lists an extra test, and I'm just not sure when that would be happening.
That might be something where I nixed it and forgot to nix it in the syllabus. So I will always give you, I mean, you got another test that opens up Friday, right? So
Yeah.
I normally let you know basically a week ahead of time. So if I add any more tests on that, I'll let you know well before a week in advance or something.
Okay, thanks.
No problem. Sorry about that. I didn't realize that I just copied and started pulling stuff out. But if you don't see it in there, then you're liable to miss it. So is that all right? Well, let's get cracking on the special theory of relativity. So I want to tell you that there actually was a special theory of relativity, and it was all motivated by Maxwell, and specifically Einstein, who loved Maxwell, knew Maxwell was brilliant, and unlike poor Maxwell, he sort of died without the all the praise of his peers. They sort of always thought of him as second good or second best because of his scoring on the Wrangler test. Even though he was the Lucasian professor of mathematics at Cambridge, that's the same position held by Newton before him. That's the same position held by Stephen Hawking and various other great minds. Dirac held that position, for instance. It's reserved basically for British scientists and usually the best of the best. Edward Witten is that position now. He's the guy that more or less gave us string theory as it currently exists. So that position is very, very well respected, but still Maxwell did not have that much respect from his peers, mainly because of that Wrangler test, but then also he introduced electrodynamics in vector calculus form. And like I said, maybe, might have been 50 to 100 people in the world that knew anything about vector calculus. So physicists just sort of paid no attention to him and thought he's a nut or whatever. So it's kind of sad. But when by the time Einstein comes along, everybody knows Maxwell was on the money, that he had really done some brilliant stuff. In fact, we can pretty much do everything we need to do with circuits, with electricity, magnetism. Almost everything we do day in and day out, we can do with Maxwell's equations. We don't have to resort to quantum electrodynamics or any of those more complex themes and theories that are based, on the quantum structure of matter. So his equations were really well understood. If you take them and do what I'd hinted at before, which is how Maxwell sort of discovered that what light was, you can make a wave equation out of it. And what Einstein realized is that wave equation, and in fact the equations themselves, were independent of the speed of light. In fact, it was independent of the speed of the experimental apparatus. So he was like, well, that's kind of weird. And he would come up with all these different problems. And like one of the things he says, he imagined shaving in front of a mirror while traveling on a beam of light and stuff like that. But when he kept thinking of these scenarios that he saw no reason that you couldn't actually do if your technology was good enough, he kept running into these paradoxes. And paradoxes are generally things that scientists do not like. If you have a paradox in your field, it is most certainly something wrong with your theory. That's generally the case. And what a paradox is it's not like Alanis Morissette's ironic or anything like that. It literally means the same theory can produce two different results, and those two results are not possible. In other words, if one's possible, the other one can't be, or if the other one's possible, then the first one can't be. That's what a paradox is, and that's unacceptable in the scientific world. So Einstein just regrouped and said, wrote his paper in 1905, and I've told you that before, like 7 papers could have all won him the Nobel Prize then. The relativity paper certainly could have. It didn't, but it certainly could have. But in his 1905 paper, he called it On the Electrodynamics of Moving Bodies. So that gives you some idea where he's coming from. So what he figured out was that Maxwell's equations were not wrong, they were right. In fact, the only way Maxwell's equation could continue to be right is if he came up with the special theory of relativity, which basically said the laws of physics are the same for all inertial observers. That's the difference between general relativity. General relativity says the laws of physics are the same for all observers, period. In special relativity, we usually include the word inertial. And what we mean by inertial is, if you recall from the first semester of this course, an inertial frame, or the law of inertia, for instance, is that an object in motion tends to stay in that state of motion unless acted upon by a net external force. And Galileo said it was as if the object has some internal inertia, some unwillingness to change its motion. That was sort of not really an explanation as much as it's just a nice pillow for you to lay your head down on, since you're smacking Aristotle in the face. So if you think about it that way, then you say, oh, well, inertial frame must be one in which the law of inertia applies. So if you affix a camera, for instance, to one of those spinning merry-go-rounds that you have in a playground, and you fix it up above the spinning merry-go-round right up here so that you only see the spinning merry-go-round, if you're watching it while it's spinning, the camera's attached to it. You don't know that it's spinning at all. You have no idea anything about it. All you know is that someone lays a basketball, say, in the middle of, or near the middle of that merry-go-round, and all of a sudden the basketball, with no objects touching it whatsoever, just speeds up and shoots off the side. For you, that would be a non-inertial reference frame because it looks like the law of inertia was just violated. An object which had no forces acting on it was suddenly thrown out the side of the merry-go-round. Okay, again, you're on a camera, so you don't, you're in a camera looking through a camera attached to the merry-go-round, so you don't necessarily know it's a merry-go-round. All you know is that that frame is something that's not inertial. Okay, so any frame in which Newton's first law of motion or Galileo's law of inertia holds, that would be an inertial reference frame. And Einstein just said, for the first principle of special relativity, the laws of physics are the same for all inertial observers. And the reason he used that to some extent is he realized by that point that gravity seems to be acting like a non-inertial thing, meaning there's nothing that reaches out from the sun and grabs the earth. There's no physical attachment between the earth and the sun, yet the sun pulls on the earth. Einstein was willing to throw that idea out and say, no, I just think the law of inertia is not applying right here, because it looks like an object, namely the earth, which was moving perfectly fine straight along and all of a sudden had to turn because it wanted to stay closer to the sun, was non-inertial. So that's what he was doing to try to cut out gravity. I'm not sure everybody knew exactly that's what he meant, but that's basically the idea we think about is the gravity introduces a apparent non-inertial frame, and that ultimately leads to 1915, him developing the general theory of relativity and it being confirmed in 1919. The other law, and this is, believe it or not, this is the weird one, the speed of light is the same for all observers. And what that means is the speed of light is the same whether you're looking at a beam of light coming towards you, whether you're looking at a beam of light attached to a spaceship traveling at half the speed of light coming towards you, or whether you're looking at a beam of light coming towards you from the back of a speeding aircraft that maybe is moving at 3/4 the speed of light away from you. All of those different scenarios, you will always measure the speed of light to be 458 meters per second. So that's a really weird thing. So that's sort of like me being on the flatbed truck, on the back of a flatbed Mack truck. Let's say my shoulder's not as awful as it is. Let's say I can still throw 70 miles per hour. And the truck's flying at 60 miles per hour down the interstate. if I'm on the back of that flatbed truck and I throw it in the same direction the flatbed truck's going, then someone on the side of the road as I'm passing by, if they took the time to measure the speed of my ball, they would say, okay, well, the truck moved by at 60, and then they measured the ball speed, and the ball would be 60 plus 70 because we're going in the same direction. So that'd be 130 miles per hour, right? That's the way what we call relativity works. And specifically, we're talking about relativity prior to Einstein. So that's what we call Galilean and Newtonian relativity. So Galilean and Newtonian relativity would suggest that, yeah, that ball thrown at 70 miles per hour on the back of a 60 mile per hour truck is going to travel at 130 miles per hour. If, on the other hand, I threw it backwards, if I threw it the way the truck's going away from, then I would be throwing at 70, the truck would be going at 60. So a person on the side of the road would dictate that, or determine that my the speed of my throw was only 10 miles per hour, but it was 10 miles per hour in the opposite direction of the truck. So that's just how velocities add. You can think of it as for every second the truck travels, it moves, or let's say, 60 miles per hour is 1 mile per second. So, or excuse me, a mile a minute. So for every minute the truck travels, it actually travels a mile. But for every minute the truck travels, the ball also travels a mile plus what it would travel as a result of the 70 miles per hour, which might be like 1.2 or actually 1.14 miles. So when you add all those up, you say, oh, well, 1.14 plus 1 in 2 minutes is going to go 2.14 miles. And if you work that out, you come up with basically 130 miles per hour. Okay, so that's the big difference. Einstein said the speed of light is a constant independent of the motion of the observer or the source or both of them. So that's a big deal. Now we can use that, and this is a trick. You've got to use it in such a way that you can actually get something worked out of it. But some of the ramifications are, I'll go ahead and tell you those up front, is you end up getting something called time dilation, which means anytime you run into someone that's moving with respect to you. So it doesn't matter if you're moving or not, in your frame of reference, you're not moving unless, you know, your body's being pulled apart or something, then some part of your body's leaving you. But generally speaking, you're set still compared to all your other parts of your body. So anybody moving by you is moving, and they're in a moving reference frame. And according to time dilation, you would recognize that their clocks are running slow. Now, it doesn't get much of an effect even at speeds of the fastest cars on the earth. But in terms of speeds closer to the speed of light, it gets to be a really measurable effect. So time literally slows down compared to your clock when you look at someone else's clock, as long as that other someone else is moving. That's one of the ramifications. Another ramification is called length contraction. And that means, like, if someone's driving by you in a Lincoln Continental, that's the big old-timey police cars they used to use back in the 80s and 90s. Really big, long cars, but they had big engines, but they were sort of like a Cadillac in terms of size and stuff. Well, if they're flying by you at 3/4 the speed of light, for instance, the direction along which they're moving, which would be from front axle to rear axle along that line, they're going to shrink this way. That's called length contraction. So that Lincoln Continental all of a sudden is going to look like a Volkswagen because its height will still be the same, but it's compressed this way. So it might look like that, or say a Nissan Cube or something. Another big thing is the lack of a firm understanding of simultaneity. I shouldn't really call it a firm understanding. It's just a lack of universal simultaneity. So just because you and I say something is simultaneous, like the instant I dropped this pen, I heard a noise when it hit the instant that it hit the table, right? That's simultaneous. There are reference frames in which two simultaneous events are not simultaneous. Okay, so that's another big one, and I'll talk about a paradox. Hopefully I'll have time to talk about a paradox later that can help you with that one. E equals mc squared, that's another result. That's the one that ultimately led us to the discovery of nuclear energy, nuclear weapons, which is neither positive nor negative, I guess, in many ways, or it's all positive and all negative in many ways as well. So we were able to get that, but that came directly from relativity, E equals mc squared. There's some other facets of it as well. Basically, your formula for momentum and kinetic energy are a little off, but Einstein's able to correct all of that. And literally, he sends in the E equals mc squared as like an appendix to the paper that he'd already sent in the day before. Like, oh, by the way, I found this. And literally that ultimately ends up, in some sense, winning the war for us in World War II, or at least ending the war. Again, historians will argue about that a little bit, so I'm not going to stick my neck out and say that's actual fact. I'll just say that some historians believe that's the case because we were able to nix it immediately and others not so much. So from here, let's go ahead and give you some examples, show you how this stuff works. I'm probably only going to do one real derivation today, and that'll be the time dilation. So let me show you my other camera. Why does it do this other times? A lot of times you put my use. Okay, so that looks fairly well focused. Hopefully my bandwidth is good. So what I want to do is try to figure out a way to make use of Einstein's principle of relativity, which is one, the laws of physics are the same for all inertial observers, and two, the speed of light is a constant independent of the motion of the source or the observer, in such a way that I can get something useful out of it. So what Einstein did was imagined a clock. And you can make clocks any way you want. All you need is something that repeats itself in time in a regular pattern. So for instance, atomic clocks use a cesium clock, where basically cesium has this decay that happens rather consistently, happens on a certain number of times per second. And once you calculate, or a certain number of times per minute or whatever, but once you hit a certain number, then that clock says, okay, it's time to flip the second over, right? So anything that repeats itself over and over again is a useful clock, or can be used to make a clock. So let's imagine, for instance, we have a train car. And this is not unlike the drawing that Einstein actually used. Okay, and in this train car, we have a little flashlight that sends out a little beam of light, and then we have a mirror up at the top. Okay, so what's going to happen is at any instant, a photon will be fired out of the actual flashlight. It's going to then bounce off the mirror and come back and hit the light, and the light's going to, hit the flashlight, and the flashlight's going to detect it. We could treat that, the time from releasing a photon to the time that the photon comes back, we can treat that as a unit of time. And as you can tell, inside of a normal train car, that would be a really, really small amount of time. So maybe we call that one train click. Okay. So one train click, in fact, might be, you might need hundreds and hundreds and hundreds of thousands of them to even make up a whole second. But it's a perfectly useful time device. So what we're going to do is we're going to define something called the proper time. And the proper time is something that is the time measured in the same place. So if you start counting the beginning of time, and then you start or stop the time that you're counting, and both events happen in the same place, then you're dealing with proper time, and it's given the symbol. In this case, we'll say delta T0. Sometimes they just call it T0, but I'm going to say delta T0. So the proper time between this photon leaving the flashlight, bouncing off the mirror, and then returning to the flashlight will be delta T0, and we can calculate that. Let's say, for instance, that the distance from the mirror to the flashlight is h. Okay. So we know that velocity equals distance divided by time. So we know that time must be distance divided by velocity. So the distance traveled for this photon is h plus h. So it'd be 2h. And according to relativity, and even without relativity, because in here the source isn't moving, nor is the receiver or anything like that, so it's automatically going to be c whether we had learned the principle of the constancy of light or not. So that's the time required for it to go from the flashlight up to the mirror and then bounce off, come back and hit the flashlight again and be recorded as a unit of time. So that's our proper time. Now here's the weird part. It turns out that a little bit later, if you're on the side of the train track, you'll see the train moving by you. And what you'll actually experience will be something like this for a person on the side of the train tracks. The person will actually see the photon of light traveling up, hitting the mirror over here, and then traveling downward, hitting the flashlight there. Okay. Now, to you, this is weird because you're seeing the beam of light going diagonally, but normally if that were just a ball or something, you'd say, oh, well, the x component of velocity is just increased by the velocity of the train car, which we're going to call v. Okay. So what we want to do is we want to try to calculate exactly how far that is. In other words, how far did the light actually travel? So the distance traveled by light, remember, velocity equals distance divided by time. So distance is equal to velocity times time. So what we'll say is that the distance traveled by the light should be c delta t. So I'm going to say this is distance by the light. And it's c times delta t, okay? Because it's always going to travel at the speed of light. So c is definitely the velocity. And then delta t is a time that's occurring in 3 different places. So at one time, the beam of light left, and it was here. Another time, it bounced off, it was here. And then a third time, it returned to the light bulb, to the flashlight and was here. So it's clearly not the proper time. Now, that's the length traveled. We can actually calculate that length too, though, because we know basically that Pythagorean theorem can give us this. So if I actually break this triangle up, I think what you'll see is this triangle and this triangle, the one on the left and the one on the right, are identical. Does that make sense to everyone? So this distance traveled from here to here, that distance is the distance that the train car travels in the first half of the time interval. So that distance would be given by the square root of h squared plus L squared, where L is basically the distance that it traveled in half that time. So that is the actual distance traveled in that interval. And then this interval is going to be the same thing. So what we're saying is this distance right here is L, and this distance right here is also L. Okay. So does everybody understand what I'm showing here is the actual distance the light traveled? That's the hypotenuse. So let me write that to the side just to make sure. So that's the hypotenuse distance. So the light beam is actually traveling the h squared plus L squared square root in the first half of the interval, and then another square root h squared plus L squared in the second half, whereas the train car only travels a distance L. So ultimately what we can see is that this c delta t, the distance traveled by the light, will in fact be 2 times the square root of h squared plus L squared. Does everybody understand that now? Does that make sense to you? Well, we know also that L is actually has to be, remember, velocity equals distance divided by time. So distance L, which is the distance traveled by the actual car in half the time interval, that's actually going to be the velocity times the time. So in fact, that's going to be the velocity of the train car times the delta t, but instead of being delta t, it's actually going to be delta t over 2. Because remember, L is only the distance it went in the first half. So from here to here is V times delta T over 2, because the whole time period from here to here, we're calling delta T. So I now can plug that back in. I get C delta T is equal to 2 times the square root h squared plus v squared delta t squared over 4. That's what happens when I square the v, the delta t, and the 2. And we're almost there. If I go ahead and square both sides, it's not going to be very hard to deal with. It just becomes c squared delta t squared is equal to 4 times h squared plus v squared delta t squared over 4. But I can distribute that 4 and it'll make it even easier. So I get c squared delta t squared is equal to 4h squared plus v squared delta t squared. In other words, by carrying that 4 through, I got rid of the 4 in the denominator, made it less fractions. So it's a word I just made up there, by the way. All right, so now I can go ahead and solve for delta t, or let's solve for delta t squared to make life simple. Delta t squared is now going to equal, notice I just divide both sides by c squared, and that will solve for t squared, or delta t squared. So I get 4h squared over c squared plus v squared delta t squared over c squared. And if I go ahead and make a substitution for, no, I don't think I will yet. Oh, no wonder. I was starting to solve for delta t. Now I'm going to get I'm going to get the delta t's on the same side. So I'll pull this over here. It'll be delta t squared.
Do you think you could scroll down, please?
Oh, yes. Thank you.
Thank
I
you.
hadn't even noticed I lost track here. So what I'm doing now is I want to get all the delta t's on the same side. So when I do that, I pull this one over here, and I'll go ahead and show you the extra step. It's going to be minus v squared over c squared delta t squared. That's equal to 4h squared over c squared. So this isn't very helpful until I factor out that delta t squared, and I'll say delta t squared times 1 minus v squared over c squared is equal to 4h squared over c squared. That h is not very helpful. This is a problem that, is supposed to be useful in all scenarios, and I've got this stupid h, which is related to the height of a darn clock mechanism in a train, right? So if I return back to my original finding that 2h over c is delta t0, I think you can see that this is the square of that. So this quantity, since delta t0 was equal to 2h over c, then this quantity right here is actually delta t0 squared. So now we're awesome. We're set up. We have delta t squared is equal to delta t0 squared over 1 minus v squared over c squared, Or finally, this is the result that we're going to be using. Delta t is equal to delta t0 over the square root of 1 minus v squared over c squared. So that's the only derivation I'm going to do today. But I wanted to show you it doesn't take any calculus or any fancy mathematics like that. It just took some basic algebra, which a good algebra 1 or algebra 2 student could probably pull off. So what it tells you is that the proper time, the time measured in such a way that the place at the beginning and the place at the end of the time interval were exactly the same. So inside the train, for instance, in this case, that divided by this square root of 1 minus v squared over c squared is equal to the time interval observed from the side of the train track. Okay. Now we also sometimes abbreviate this and say that delta t is equal to gamma delta t0, where gamma is defined to be 1 over the square root 1 minus v squared over c squared. So that's a thing that you'll occasionally see, and it'll certainly save you a buttload of writing. We'll even sometimes replace v over c with beta. So you can just say 1 minus beta squared if you wanted to. So those are two ways you can actually make your life a little easier if you're doing algebra, is just, get rid of that gamma for a little while. I mean, get rid of that 1 over the square root of 1 minus v squared over c squared and just call it gamma. Or if you're messing with v over c, just keep calling it beta until the end and you can put it back in. So that's kind of nice. Let me work an example. Let's say a muon is known to be produced in our upper atmosphere. And it travels at, let's just, I'm going to choose a number that's kind of nice. I'm going to say square root of 3 over 2 times the speed of light. That's a really nice number. The reason why I say it is because when I put it in here, I square it, that becomes 3/4. And 1 minus 3/4 is an easy fraction that I can deal with. It'll just be 4/4 minus 3/4, which is 1/4, and the square root of 1/4 is just 1/2. So we get really nice numbers, in other words. To get a physical feel for what that number is, all you really have to do is calculate the square root of 3, which is 1.73205, and then divide that by 2, and you get 0.866. 0.8666025. So that's a nice little trick we can use. There's a lot of different values of V that you can use to give really nice results. And the muon, that's the symbol they use for it, has a lifespan of only 2.2 microseconds. Okay. And that's measured inside of a lab frame. So if you're just sitting there right next to the muon and you see it created and the muon's not moving and you're watching it, it's going to die in 2.2 microseconds. That means it's going to actually decay into something else. Okay. That is a proper time, for instance, because the death and life of the muon happen in the same place. So the question is going to be, how long will it live? This is A. How long will it live flying through our atmosphere? And then part B, how far will it travel? Okay. So that's a pretty reasonable problem. It's pretty straightforward. What we're saying here is that there's this muon. This is reality, by the way. This is one of the first ways we were able to prove that Einstein was right, because we had this weird mystery going on where we know that muons are created in the upper atmosphere, but we also know that their lifespan was too short, given how fast they were going, for them to actually reach the surface of the Earth, but we kept detecting them at the surface of the Earth. So that, begged the question, how in the heck is the muon making it to the surface of the Earth if it doesn't live long enough, given its speed, to actually make it here? Meaning, if you multiplied the speed times its lifetime, the distance is less than the thickness of the atmosphere. So how the heck is it getting here? So what we're going to do is we're going to try to calculate really what our time is. So in other words, when we're sitting here and watching the photon move by us, right, what we see is that that muon's life stretched. Remember, a moving clock moves more slowly. So you can think of the muon as if it had a heart and it's only allowed, 2,200 heartbeats. Okay. So to us, those heartbeats would take a lot longer because it's moving than it normally would, because moving clocks move more slowly. So what I'm going to do is I'm going to write right along here. I'm going to say delta t, this is part A, delta t equals question mark. And delta t is actually equal to delta t0 over square root 1 minus v squared over c squared. Well, delta t0 is the proper time interval, and that's how long the photon or the muon lives in its own reference frame. And that is 2.2 times 10 to the negative 6 seconds divided by 1 minus, and I'm going to put it back in this nice fractional form, square root of 1 minus square root 3 over 2 c over c, and all that quantity will be squared. So what I really did is I substituted for v, I substituted square root of 3 over 2 times c, and then of course that's on top of c, so that's why you see the c's there, and everything's squared. Kind of hard to read, but that's root 3 over 2, and that's c over c. Definitely need to be my decimal points a little better. Okay, so this is 2.2 times 10 to the negative 6 seconds. And then what I get is square root 1 minus 3/4, which is really easy because it's 2.2 times 10 to the negative 6 divided by the square root of 1/4, which is in fact 1/2. So I end up getting 4.4 times 10 to the negative 6 seconds is the lifetime. So notice it'll live twice as long. Notice it'll live twice as long because it's moving according to our reference frame. So we'd say, oh, well, yeah, it's not supposed to make it to the surface of the Earth, but because its clock's running slower, it lived a longer life. Therefore, boom, it hits our atmosphere. Or, excuse me, boom, it hits the surface of our Earth. Okay. Now for part B, which I'm going to go over here to do. So for part B, they want to know how far it's going to travel. So I'll just call that L equals question mark. Well, L is just velocity times time. Okay. Now this is our time because in its frame, it's not moving. To the muon says, hey, I'm not moving at all, so I didn't go anywhere. The Earth came rushing at me, in fact, is what happened. So what I'm going to do is say 0.866, and I can even go 0.25 c times 4.4 times 10 to the negative 6 seconds. So I'm multiplying all these numbers. Remember, I've got to include c, which is 3.00 times 10 to the 8th. So I'll call it 0.866 times 3 times 10 to the 8th times 4.4 times 10 to the negative 6 seconds. And when I do that, I'm going to get 0.866 times 3 EE8 times 4.4 EE negative 6. And I get 1,143 meters roughly. Now I really should round this to probably 1.1 kilometers. And that's, you know, I completely made up the speed for convenience, but you can see the point is it's definitely going to travel twice as far because of this time dilation than it otherwise would. And that would, you know, probably given the speed that it actually did travel at experimentally, that would explain why it hit the surface of the Earth. Of course, the laws of physics must be the same for all inertial observers. So we still got a little bit of a problem. Maybe y'all thought about it already. So in our frame, the muon's moving at, you know, 0.866 times the speed of light. And therefore its time is dilated. So from our standpoint, it lives longer than it should. So it actually is able to travel 1.1 kilometers instead of the otherwise 15 or 560 kilometers, or excuse me, 560 meters. But what about the muon? In the muon's frame, can anybody think why the muon understands that it actually hit the surface of the Earth? Does anybody see a incongruity here? I'm not trying to give you any hints. I'm just making sure there's plenty of footage of this sheet in case y'all have to look back at the video to try to figure out what was done and all that good stuff. So I'm just giving you another chance to see everything. Okay, that's okay. No one ever gets that question right, but I always ask it just in case someone really gets excited about it. So here's the deal. Both the muon, even though it's not a sentient being or anything, but both the muon and us have to agree on what happened in the experiment. And the experiment was we created a muon at the upper edges of the atmosphere. And that muon, of course, was created due to the energy of the sun hitting certain particles and causing certain decays and so on and so forth. But the final part of the experiment was that the muon hit the surface of the Earth. And both us on Earth who saw it happen have to agree, both us and the muon itself have to agree that it started in the upper atmosphere and that it died on the surface of the Earth. As it is right now, there's no way we could possibly understand it from the muon standpoint. Well, at least not mathematically yet. So from the muon standpoint, the muon is sitting perfectly still. So how the heck did it make it? It knows it's sitting perfectly still. It knows the Earth is moving towards it at 0.866 C. You know, it can do that experiment. And it multiplies its lifetime times 0.866 C. And it gets basically, here, I'll do it for you. 0.866 times 3 exponent 8 times 2.2 exponent negative 6. So according to the photon, or excuse me, according to the muon, it only makes it 572 meters. But it knows for a fact that the atmosphere is not 572 meters because it actually read a publication that we put out some time ago. Okay, we the humans of the Earth. So something's clearly missing in relativity. Well, that thing that's missing in relativity is another aspect that I told you was a result of the special theory of relativity, and it's called length contraction. So length contraction is sort of the opposite. We have time dilation, which says the time observed by someone watching someone moving is equal to the time the moving person experienced times gamma, which would be 1 over the square root of 1 minus v squared over c squared. Okay, but we also know that there's something called length contraction, and we could write this, for instance, delta t is equal to gamma delta t 0. Well, length contraction, we can write the other way. We can say delta, or let's just call it plain L, say. Let's say L is equal to L0 over gamma, and that would actually be exactly right. In fact, the way your book writes it is L is equal to L0 times the square root of 1 minus v squared over c squared. Okay, so remember, gamma is always going to be a number. Remember, when we computed gamma, we got 1 over the square root of 1/4, which is 1 over 1/2, which is 2. So gamma is always, always, always. That's something to help us. So when I say the proper length, according to, in other words, the muon, if the muon actually went out and measured what that distance was, it measured the distance in a very special way, and that proper length, when you divide it by a number greater than 1, is going to be smaller. So us people here that are watching that muon fly by would say, or the other way around, I should say, are basically going to find length contracted. Okay, so here's the wording that is often used. The length of an object moving relative to an observer is measured to be the shorter along its direction of motion than it is at rest. Okay, so the rest distance, the distance of it when it's sitting still, is going to be actually longer than the length that it'll be when it's moving by you. So now we can go back and answer the question why the actual muon was able to reach the surface of the Earth. In the muon's frame, I told you the Earth was moving towards it at 0.866 c, and of course the muon did a calculation and found that it should only make it 572 meters, which is not far enough, according to the paper it read, where Earthlings had measured the depth of the atmosphere. But then the muon learns a little bit more about relativity and says, hey, wait a second. Yeah, maybe that atmosphere is 1,000 kilometers thick, but guess what? I see the Earth and the atmosphere coming towards me at 0.866 c. So in my frame, I'm going to find that that Earth that's moving towards me actually has a atmosphere, instead of it being, let's say, 1,000 kilometers. I'm just going to pretend like the answer is 1,000 kilometers. Instead of it being 1,000 meters, it's actually going to be 1,000 divided by 2, because gamma, remember, is 1 over the square root of 1 minus root 3 over 2 c over c squared, which was 1 over the square root of 1/4, which is 1 over 1/2, or excuse me, 1 over 1/2, which ultimately became just 2. Okay, so with that we say, oh, well, in the muon's frame, the atmosphere was only 500 meters thick, or 0.5 kilometers thick. Hence, I hit the surface of the Earth because the atmosphere was Lorentz contracted. This is why I said for a second there, this is the muon's length, and then I said, well, it's actually the opposite of that, but I'll explain. So that's what happened when I was talking about here. So in the muon's frame, the length, the proper length, is any length that measures with the thing not moving. Okay, but in the case of the muon that for us was flying towards the Earth was the actual thing moving. So the dilated length is the length of the atmosphere according to the muon's frame. Okay, so let's look at some of these other ramifications. So that's the first two, and like I said, this was something that was a confirmation of Einstein's special theory of relativity, which, by the way, I did mention he did not win the Nobel Prize for. He won the Nobel Prize for the photoelectric effect, a little interesting historical tidbit. Him and his wife were both physicists. His wife was brilliant. Then, of course, he ended up leaving her later and married his second cousin. And his second cousin was not a physicist, but she was really good at just doing the chores. So that's more or less what he was looking for, was someone that was convenient. But sadly, he left his other wife, but him and his other wife both knew that what he had done in 1905 was amazing, so much so that when they were settling their divorce, Einstein said that he would give her his Nobel Prize winnings. And she took that, and of course he did. He gave her his whole Nobel Prize winnings, which, you know, nowadays Nobel Prize winning is it's either 1 or 2 million, but it was a lot less back then. But it was the same amount dollar-wise because it goes up accordingly. So imagine that Einstein gambled that, hey, I'm going to get the Nobel Prize, and you can have the money if you just let me leave this marriage. And she was like, yeah, I know enough about physics that I know you're going to get the Nobel Prize. So it's a kind of interesting, I mean, sad, because, you know, obviously when a marriage falls apart, sometimes it can be quite sad. And they did have a child, so that was even worse. But she was seemingly had some major mental illness, and that took its toll, as well as Einstein was not an easy person to live with, I'm sure. He was extremely, extremely obsessive compulsive and stuff of that sort. So let's look at some issues regarding special relativity. First off, what I want to see is time dilation relevant to everyday life? In other words, are we getting any massive effects out of it for earthly travel? So what I would argue when I'm going to try to address such a question is I would say, well, what's the fastest speed we can do right here on Earth right now? And then I'd see what's the effect of time dilation in that scenario. And if I see that it's an appreciable effect, I go, wow, well, yeah, that's pretty cool. Okay. If I don't, though, then I say, okay, well, we're probably never going to accumulate any benefits from this. So what I'm going to do is I'm going to share my screen real quick and show you how I do some of the stuff that I do. I'm going to look right here. So I'm going to share this screen, which isn't really that helpful. But now I'm going to go right here, fastest land speed record. I want to say it's on the order of 700 miles per hour or something like that. Yeah, 763 miles per hour. Are 1,227.985 kilometers per hour. So let's consider V equals 600. I'm going to use both of them so we can. I'm going to say 763 miles per hour, which equals. I'm just going to use 4 sig figs on this one. 1,228 kilometers per hour. And I'm going to say, how long is a 10-second interval changed? So let's say a person in the car driving this fast, which if you're driving this fast, you really need to not be messing with your watch and phone and stuff. It's bad enough at 30 miles per hour. Imagine it at 760 miles per hour. But let's say they take a time period of 10 seconds. Okay, what I want to know is what is delta t? In other words, how much time do we see pass on his clock? So we got a telescope, we're looking into his cockpit of this fancy racing car, and we're going to try to determine how slow his clock's moving. So we're timing what takes 10 seconds in his interval and seeing how long it takes ours. So here's how we do it. We go delta t is equal to gamma times delta t0, which equals to 10.00 seconds. And actually, let's carry an extra decimal place just in case we need it, okay? And then we're going to divide that by the square root of 1 minus. Now I got to make the velocity, but I got to make it in the same units as the speed of light, which is, 3.00 times 10 to the 8. I'm going to actually use it more precisely too. So let's say it's exactly this speed. What I then know is that 1 hour is equal to 3,600 seconds, but that's the wrong way because the hour would not cancel out with the hour. So I multiply, let me do it over here to make sure everybody sees what I'm doing, 1,228 kilometers per hour. What I do is put 1 hour up top, and that corresponds to 3,600 seconds. And then I take the 1 kilometer, put that on the bottom to make sure it cancels out with a kilometer on the top, and that's 1,000 meters. So basically, at the end of all this, I'm going to divide it by 3.6. So,
we
ma'am.
only see the screen that you're sharing. Can you?
Right, I know you're not looking at that. Yeah, I was just getting ready to put it on there. Thank you, ma'am.
Thank you.
No problem. So let me go here. I will flip back to this. So now that we have our, I think I just did, okay. Oh, I did this first. Okay, gotcha. Okay, so now that I have this, I just took the 3,600 seconds and 1 hour. That's a fraction equal to 1 because the top's equal to the bottom. I could have did it in either order, but by doing it this way, the hours cancels out with the hours, and the kilometers cancel out with the kilometers when I do it that way. So basically, I'm just going to do that 1,228, and I'm going to divide it by 3.6. And I get 341, which I think y'all recognize is faster than the speed of sound, basically 341.1 meters per second. So I want to try to use 4 sig figs on everything at least. The speed of light, however, C is 299 and then 792. I think it's 792. Yeah, 792. 458 meters per second. So really what I'm doing is I'm going to take 341.1 meters per second and divide it by 299,792,458 meters per second. And then I'm going to square that. If you actually try to do this though, it's ugly. And in fact, you can't really do anything with your calculator because it's basically just going to call this quantity 1. Okay, so when I do on my calculator, I do 1 minus, now I do parentheses, 341.1, and I divide by, and I have actually a very expensive calculator with a buttload of digits is available. Let's see what happens. I'm going to divide that by 299,792,458. And then I'm going to square that quantity. And my calculator spits out 1. Okay. So I'm obviously going to get just 10 seconds. But if I do something, we have this thing called the binomial theorem, which basically tells you that if you have an expression 1 plus x to the n power, you can approximate this by using more and more terms to get as close as you want to, but it becomes 1 plus n times x plus 1/2 n times n minus 1 times x squared, as you can imagine, plus 1/3 n times n minus 1 times n minus 2 times x cubed, so on and so forth. All that stuff goes on forever and ever. We're going to use this expansion to basically treat 1 minus beta squared, the square root. That's the same thing as 1 minus beta squared to the negative 1/2 power. So we're going to use that expansion. So notice we're replacing x with basically negative b squared. So that will be 1 minus b, or 1 plus negative b squared, and that's to the negative 1/2 power. That's how we're going to substitute this. So our answer is going to be 1, and then n, of course, is negative 1/2, so it'd be minus 1/2 times x, which is negative beta squared. Now I can do more terms, but I think this is going to be plenty good. That first one will be the biggest one, and they get smaller and smaller as you go on. So I'm going to try to do that now. So this will become 1 plus 1/2 of 341 over 299792458 quantity squared. Obviously that 1 is going to stay, but now I can do 341.1 divided by 299792458 equals, I can square that. It's 1.295 times 10 to the negative 12th. So if I divide that by 2, because I have this 1/2 here, I get 1 plus 6.473 times 10 to the negative 13. So now our delta t can actually be made sense of. Our delta t is going to be equal to 10.000 seconds times 1 plus 6.473 times 10 to the negative 13th. And these are all dimensionless quantities, all this stuff is. So you see it's basically going to be 10 seconds plus 0.000000000, that's the 12th, 6473. So do you think relativity is something that's relevant to our everyday velocities? Probably not, right? You'd have to use an atomic clock just to tell the difference. So in other words, way out in the 13th decimal place, I've got a 6 there instead of a 0. So it's 10.00000000006 instead of 10.000 forever. So it's literally only gaining 6 to the 13th decimal place every 10 seconds. So it's not very relevant. In fact, 10 to the 13th seconds is basically on the order of what? 10 to the 7th would be a year. So that's on the order of 1,000,000 years. So basically, you wouldn't get a whole second out of it for doing this for like 1,000,000 years. So it doesn't add up appreciably over time. You know, the fact that I drive back and forth between North Carolina and Virginia at 60 miles per hour or so for an hour each way, hour and 15 minutes each way. Yes, I'm getting time dilation advantages, but those time dilations are so teeny weeny that I'm still gonna die at the same old time essentially. Any questions on that? All right, so that's a everyday thing that you should be able to consider is, how does the speed of light compare to average speeds or even to the most phenomenal speeds? I just compared it to the most phenomenal speed, and the most phenomenal speed is on the order of 341 meters per second or 763 miles per hour. That's really, 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 really fast. And still, I only got a change in the time dilation way out in the 13th decimal place. If you wish to say, let's say we're flying you are flying in a spacecraft at 0.866 times the speed of light, okay? And you read for 100 minutes. Okay, so 100 minutes, that's an hour and 40 minutes basically. How long would your friend at the space station to which you are going say you read if you had called just before and immediately after? Okay, so we're going to ignore time delays with the communication between the friend and you. But say you're traveling at 86.6% of the speed of light. That's a very special beta. That's a beta that gives us a very special gamma, which is 2, of course. So it makes the math really easy. So what we're trying to figure out is you get on the spacecraft and you say, hey, you call your friend up and say, hey, I'm going to go ahead and read. I got a little spare time. It's quiet in here. I don't have some jerk sitting next to me wanting to talk about my career or anything like that. So I'm going to read for a while, and I'll call you when I'm finished. And your friend at the airport says, okay. And then you call them back after you're finished, and you had realized you'd read for an hour and 40 minutes, which is a pretty good stretch of reading. What you want to know is, what does your friend sitting at the airport, how long does he think that you read? So the big deal is here is figuring out whether the 100 minutes is proper time, or is it the other time, the dilated time, okay? And can anybody tell me that? Do y'all know whether the 100 minutes is proper time, or is that dilated time? I'm watching the chat too, in case anybody wants to type it in. Okay, looks like no one has a guess. So remember, proper time is the time measured when you measure the beginning and end at the exact same place. So she was clearly sitting in her seat, or you were clearly sitting in your seat when you called your friend and then started reading, and you were clearly sitting in your seat on the same spacecraft, of course, when you stopped reading and then called your friend. So clearly the 100 minutes you spent were measured at the same place. So that's your actual proper time. So your friend's going to think you read a lot more. So in fact, delta t is equal to delta t0 times gamma becomes delta t is equal to 2. There's the gamma factor. That's because we used 0.866c times the proper time, which would be 100 minutes. So 200 minutes went by for your friend at the airport, or the space station, I should say. So in fact, a 100-minute read, according to your friend at the space station, would turn into a 200-minute read. Now the bummer is your friend thinks, well, crap, in 200 minutes, she should have got a lot of reading done. Well, your clock slowed down, so you read way slower, so you still read about as much as you normally read in 100 minutes. But your friend would be like, wow, you could have read a lot more. So anyways, That's another neat problem. That's another neat conceptual issue regarding special relativity. Basically, that time dilates makes things happen kind of weirdly. I'm going to go ahead and give you guys a break. Let's meet back at 11:05. Right here at the same one, but we'll meet back at 11:05. I'm going to turn my camera off again and my recording off, but y'all are welcome to ask me questions. I'll be right here.
Professor Younger.
Yes, ma'am.
So for gamma, is it always going to be equal to 2 or just when it's the 0.866?
Yeah, just when it's the 0.866, and it's a good practice for you to like take a bunch of values. Like your book has a table, for instance, of velocity equals 0. Obviously, that's gamma going to be equal to 1. You could do 1% of the speed of light and see what gamma would be, 10% of the speed of light, half the speed of light, 90%, 99%, 99.9%. I would recommend calculating those for those speeds just to get a ballpark figure for what gamma would be every time. But yeah, every time you use 0.866c, gamma will be 2.
Okay, thank you.
Okay.
Professor Younger,
Yes.
earlier when you did the roll, did you get me down? I heard you calling everybody's names to confirm if they were there, but I had stepped outside to talk with my mom for a second.
Okay, what was your name?
Owen Rubin.
Yeah, I think I did get you. Let me double check though.
Yeah, I have been here the whole time. I just stepped out for half a minute.
Yeah,
And
it's
I
not,
think
not
you
a
missed
big deal,
mine.
bud. Let me see, lecture roll. I'm pretty sure I got Owen because that's a distinct name. I have a friend named Owen. Yeah, Charles, who I did not get, and Christian I did not get, but Owen I did get.
Okay, thank you very much.
No problem. Anybody else have any questions? All right, good deal. Well, like I said, y'all come back at 11:01. I'm just going to kill the camera for a second. So does anybody have any questions about the two things we just finished calculating? Basically a length contraction and a time dilation. So the big things are, I'm going to write them up here again just as a refresher. We've got delta t. This is the dilated time is equal to the proper time, delta t0, divided by the square root of 1 minus v squared over c squared. Of course, we can use the simplification that gamma is equal to 1 over the square root of 1 minus beta squared, if you wanted to, that where beta is equal to v over c. That's about as succinctly as you can write it. And then we also found that the proper length, L0, is equal to gamma, or excuse me, the length over gamma. Actually, I think I wrote that backwards. Let me double check real quick. I'm about 99% sure I just wrote that backwards like a dummy. Yes, I did. Thought so. The deal is it's the opposite formula. So if you have it times gamma, then it has to be times the regular length. Whereas if it's divided by gamma, it has to be L0. So we'll write L is equal to L0 over gamma. See how the gamma is either multiplied by the proper or it's divided by the proper. My daughter is calling. Okay, so those are the two major formulas we figured out. The proper time, again, is the time measured by someone who has both the beginning and the end of the time interval occurring at the same place, meaning the same place with respect to them. That place, for instance, could be inside a spaceship. And if they didn't have to measure at two different locations, then clearly that's the proper time. Whereas like if you're trying to measure the time for a spacecraft to fly from one place to another, then you measure the beginning of the time at the beginning place and the last of the time at the ending place. So that's two different places. So that would be the dilated time. Okay. the proper length is the time measured, or excuse me, is the length measured that could be done both in simultaneously. Okay, so that's another little neat trick. Whereas if someone's flying by you in, say, a spacecraft, what you're going to do is stand still and mark the beginning where the bow of the spacecraft gets to you, and then you're going to sort of run along and then try to measure when the bow or the rear of the spacecraft gets near you. So you're measuring it at actually two different locations in that case. So that would be that would not be the proper length. That would be the contracted length. Okay, so hopefully that helps you a little bit. I thought I'd work a sort of interesting problem. So if you've ever seen a Nissan Cube, it sort of looks like this. So that's a Nissan Cube. I roughly measured it. Turns out that windshield is about 30 degrees. And then the opposite end of the spectrum is this really sweet Ferrari called the Ferrari Roma. And it turns out I measured this angle for the windshield is about 60 degrees. Okay. So remember, if this car is traveling this way, its contraction will only be along this axis. Similarly, if this car is traveling this way, its contraction will only be along this axis. So this height will stay exactly the same, but this length will change. Same thing here. But what we could do is we could say, I wonder how fast the Ferrari Roma has to go before its angle of windshield matches that of the cube. So that's the kind of interesting little problem. So what we'll do is we'll take the Ferrari Roma, and let's say this angle, we know for a fact when it's sitting still, this angle is 60 degrees. That means, of course, this angle is also 60 degrees. And we could use the 60, 30, 90 triangle. And then that would mean this, of course, is 30 degrees. And then, of course, the 60 degrees is opposite the square root of 3. And then the 30 degrees is opposite the 1. And then this would be the square root of, or excuse me, this would be the, yes, 2. Okay, so that's the 30, 60, 90 triangle. So let's imagine now that we have a windshield that is 1.73, let's say decimeters or something, okay? This way. This height right here is just 1 decimeter. And then this, of course, is the windshield. Then we know that that is 60 degrees, which is also this is 60 degrees, okay? So this is just a zoom in of this part. Roughly using those units, I've automatically fixed these sides, whether the decimeter is true or not. It's the main thing is I fixed it so that it's a 60-degree angle, and I need to find out how fast it has to go for this thing to flip and become, in fact, a 30-degree angle. This side is still going to be 1 decimeter, excuse me, but this is now going to be 30 degrees, so this would be 60 degrees. Okay. So if this is 30 degrees, this is the opposite side, and this is the adjacent. This is 60 degrees, excuse me, this is the opposite of it, and this is the adjacent. So tangent 60 equals 1 decimeter over question mark. If I can get what 1.73 is to reduce down to whatever this figure is, then I'll have the Roma's windshield at 30 degrees instead of 60 degrees, and of course it'll make it an ugly car. So we say that the question mark is equal to 1 decimeter divided by tangent 60 degrees. From here we know that tangent 60 degrees is root 3 over 1. Remember, this is 60 degrees right here. So opposite over adjacent is root 3 over 1. So it's equal to 1 decimeter over 1.733, or 1.73 meters, roughly decimeters. Oh, and that's not decimeter, by the way. It's just a unitless number. So when I calculate that, I'm going to go back to using actual square root of 3 instead of the 1.73. That way it'll come up a little more precisely. So I'll say 1 divided by square root 3, and that's 0.5774 meters. So if I can contract the 1.73 down to 1.55, or excuse me, 0.5774, then I will have this Roma with a windshield as steep as the cubes. So it'll look obviously more goofy. So let's do that. What we have is, we have a proper length of 1.73. So the L0 is 1.73. Again, I should really check how many digits that's to. Let's say the square root of 3, 1.732 decimeters is the proper length. And I want the actual length that you measure as it flies by you. I shouldn't say actual, I just should say the contracted length. I want that to be 0.5774 decimeters. Then what I need to calculate is how fast it must go. So I want to know V equals question mark. Well, I know L is equal to L0 over gamma. So what I could do is I could say L0 over L is equal to 1 over gamma. Just solving this for L0 over L. I divide both sides by L, and then I multiply both sides by gamma. It's just equal to gamma, sorry, not 1 over gamma. So multiplying both sides by L, or excuse me, dividing both sides by L, I get L0 over L, and it cancels out over here. But the gamma is still on the bottom, so then I multiply by gamma on both sides, and I get gamma on the top and L0 over L here. So that makes it right. So what I want is 1.732 decimeters over 0.5774 decimeters. I want that to be L0 over L. So 1.7 divided by 0.5735 gives me roughly 3. Duh. Okay, it gives me exactly 3 if you want to use the math right. So I need a gamma factor equal to 3. So what I say is 3 is equal to 1 over the square root 1 minus beta squared, just using that beta for right now because it's less crap to write. Okay, so setting beta equal to this, I square both sides. I get 9 is equal to 1 over 1 minus beta squared. I multiply both sides by 1 minus beta squared, and I divide both sides by 9. I get 1 minus beta squared is equal to 1/9. And then I add beta squared to both sides, and I subtract 1/9 from both sides. 9/9 minus 1/9 would be 8/9. And the other side is just going to be beta squared. So that means beta is going to equal the square root of 8, which would be 2 root 2, over the square root of 9, which would be 3. So that means V should equal 2 root 2 over 3 times C. And 2 root 2, let's see, 2 times square root of 2 divided by 3 is 94.28, 0.9428 C. So it's 94% of the speed of light basically is required. So if this Roma happens to travel at 94.3% of the speed of light, then it's going to go from this really sleek looking car with the really low profile windshield like that to exactly the same height now, but everything's going to be contracted by a factor of 3 basically. So it's now going to be about this long, The wheel would be there. This would be there. Oops, didn't drop tall enough. So it looks something like that, meaning this height and this height and this height should all be the same. And the wheels, in fact, will be quite ellipsoidal, or at least elliptical, because the diameter this way is going to contract, but the diameter that way is going to be exactly the same. So any questions on that problem? So if you want the windshield angle to switch from 60 degrees to 30 degrees, you're going to have to make it travel at 94.28% of the speed of light. So that's a pretty impressive one. That gives you another beta that can be useful, by the way. Square root 2 over 2, or square root 2 times 2 over 3 gives you a nice even beta factor of 8/9, square root 8/9, and a nice gamma of exactly 3. So it's cool to find out. What I recommend you guys is what I was telling you just a few minutes ago, is find gamma when beta is equal to 0.01. That means 1% of the speed of light. Find it when it's 0.1. That's when it's 10% of the speed of light. Find it when it's, let's say, 90% of the speed of light, 95% of the speed of light, 99% of the speed of light, 99.9% of the speed of light, and 99.99 of the speed of light. Find out what gamma is on all those things. And, you know, the smartest way is do it with a spreadsheet. That way you take the formula once and then you spit out the answer. And then you can go back and try, okay, well, what is beta when gamma is equal to 2? What about 3? What about 4? What about 5? What about 6? What about 10? Okay, so then find beta in those cases, and you'll have a good feel for the contractions and length contractions and time dilations that could actually occur. You might even want to just do 1, 2, 3, and 5 and jump up to 10, 100, 1,000, something like that. So those are all cool. And like I said, the best way to do that would be with a spreadsheet, because whenever you're repeating a calculation over and over, you're crazy if you're not doing it with a spreadsheet, because you're just, you know, that's exactly why we were given computers, to do things mundane where we're going to make a bunch of mistakes and make them trivial to calculate and make no mistakes. All right, so the last couple things we're going to talk about with relativity is there's this concept of space-time. So normally we deal with, like in physics, we normally deal with a two-dimensional universe. We talk about a X and a Y, where X is forward and backwards, say, and Y is up and down. Even though we know in reality we're dealing with 3 dimensions, there's a X, there's a Y, and then using the right-hand rule, that would mean a Z is pointing out of the page. And that's fine too. But if we just talk about, for instance, one-dimensional motion, then everything could be handled by the X direction, right? So what Einstein was able to do was he was able to make more sense of his equations, as were other people, Minkowski and other people, were able to make more sense out of his equations for special relativity by looking at space as if it's 4-dimensional. And what that would mean is you still have X going forward and backwards, you still have Y going up and down, and you still have, let's say, Z going left and right, right? But now you add another dimension, time. So if we're dealing with one dimension, we could actually represent that really well. And oddly enough, we find that it's better to do it X on the horizontal axis and time on the vertical axis. Okay, that's sort of the beginnings of space-time, if you will. So space-time really is an X, Y, Z. Basically, you imagine every point in space has a little X, Y, Z axis, but then you'd imagine a mutually perpendicular axis to those 3, which you can't imagine because it requires 4 dimensions, and we can't see in 4 dimensions. That would be a time dimension. But what you can do is sort of associate it with an X, Y, Z axis with a little clock built in, and then you have space-time. So as long as you have a way of measuring the 3 dimensions and time, then you have the ability to do space-time. When Einstein did that, he discovered these things that are called 4 vectors, which you know, he'd already knew about to some extent, thanks to some of his people that he worked with in school, who basically, like Marcel Grossman. Einstein had sort of checked out during his math class and just went and drank coffee and talked about Spinoza and other philosophers all during his math class. And it was a shame because he actually got to learn differential geometry and tensor calculus and stuff like that. And then when relativity, he decided to write a paper on that, he realized he couldn't, he realized he basically couldn't do the math. So he went back and talked to his friend Marcel Grossman, who actually paid attention in the class. And that guy had his notes. So he read all that through that stuff. Einstein taught himself basically tensor calculus and everything that was needed for special and general relativity, but especially general relativity. That math teacher was the one, if I remember correctly, that called Einstein a lazy dog. But that really was about the only time that he was, quote unquote, said to be not very bright or anything like that. They thought for the first several years of his life, at least according to family lore, that basically he did not speak for the first like 5 years of his life. He literally didn't say a word, but when he did start talking, he spoke in whole sentences. So that was the only other instance where someone thought he was below average or something was wrong with him. Or so a lot of the stories you hear about him being in a failing math and stuff like that wasn't really true. He just had that one instructor called him a lazy dog. So it turns out when you actually do that, you can find out a lot of new things. It turns out there's other formulas in addition to length contraction. There's something called momentum, which you learned about before. Before we said momentum was mass times velocity. Well, it turns out that mass times velocity doesn't obey the law of conservation of momentum. It also has problems with the law of conservation of energy. So Einstein was able to actually fix that once he had his equations for special relativity. And what Einstein discovered is that the magnitude of momentum is actually gamma times m times v. So that's kind of a neat little thing. Notice the difference. That's that same gamma 1 over the square root of 1 minus v squared over c squared. That is the same one. And what you see is the faster you go, and this is the way I like to think about it. I don't like to think about this as a relativistic mass. The faster you go, the bigger this number gets. Remember, because this is 1 over the square root of 1 minus v squared over c squared. And I told you gamma is always 1 or greater. And you saw as gamma got closer and closer to 99% and so on and so forth, or to, you know, as beta got closer and closer to the speed of light, or 1 basically, the gamma became really, really large. So this is one of the reasons we say an object with mass cannot go even at the speed of light, much less exceed the speed of light, because it's as if the momentum is getting infinitely larger. And when you use this momentum, then Newton's second law of motion, F equals this form, by the way, not the way we learned it, but the way that Newton actually wrote it, delta P over delta T. When you use this, you see that as you want to change delta P, it gets infinitely hard as this becomes infinity. So in fact, it takes an infinite amount of force and therefore an infinite amount of energy to bring anything with a mass that's not 0 to the speed of light. So we'll never, ever, ever reach that. But you can check different things like what is the regular momentum, P equals mv, for an electron. Let's say we have an electron traveling at, I don't know, let's say it's about a 10th of the speed of light. Let's say it's about 2/3 of a tenth of the speed of light, so about 0.6 of the speed of light. So let's say we have an electron, m sub e is equal to, its mass is 9.109 times 10 to the negative 31st kilograms. Okay. Let's say its velocity, speed of light is 3 times 10 to the 8th. I want to do about 0.6 of that. So 0.6 times 3 would be 1.8. So I'm going to call that roughly 2 times 10 to the 7th meters per second. So classical momentum, which I'll call PCL, would say the electron has a momentum of 9.109 times 10 to the negative 31st kilograms. And this is a horrible unit, by the way, to use for momentum for such small particles. We really should be using stuff like MeV per C or something like that. And then 2 times 10 to the 7th meters per second. And what we get, and this is what we normally get last semester when we were doing the minimum calculations, what we get is 9.109 e to the negative 31st times 2 e to the 7 is 1.82 times 10 to the negative 23rd kilograms meters per second, which I think you can see a kilogram meter per second squared would actually be a Newton. And if you added another meter, it'd be kilogram squared, meter squared per second squared, meter squared per second squared. Then you'd actually have a Newton meter, which is a joule. And obviously that's the difference of meters per second. So you could actually divide out that. And that's how I was talking about the unit would be a EV per C. Now with that, let's calculate what gamma will be, because we need P to be gamma MV. So gamma would be 1 over the square root of 1 minus, and this time we're going to do 2 times 10 to the 7th meters per second over 3 times 10 to the 8th meters per second, and then we've got to square all that junk. I think you see what happens. That's 2/3, that'd be 0.6 for 2 divided by 3, and then 10 to the 7th, of course, divided by 10 to the 8th would be 10 to the negative 1. So it'd be 0.6 divided by 1, or 0.06. So we get 1 over the square root of 1 minus 0.06666 squared, which is equal to, the way you work this with a calculator is usually best to start in the innermost. So I'll say 2 exponent 7 divided by 3 exponent 8. Then I square that. Then I do 1 minus the answer. And then I take the square root of all that. So root, again, the answer. And I get, oh, I forgot to, now I invert that. I say 1 divided by answer again. I ended up getting 0.997775. And remember, gamma is always bigger than 1, so I knew something was up. So in fact, we get 1.00223. Okay, so that's what our gamma factor is. That means 1.00223. I'm carrying all these extra digits just in hopes we can see where the change is. 1.82 times 10 to the negative 23rd kilograms meters per second. So times, 1.82 e negative 23. Gives me 1.82 times 10 to the negative 23 again, which obviously is not that big a difference, but you can see it's, in this case, it's 1.8. This one was 8.2. Actually, let me scroll up a little bit, see what the other original one was, so I can keep extra digits. This one was actually 8.218. And it turns out this one's actually 8.2406 times 10 to the negative 23. So you can see it comes up. It is a difference, but it's a difference way out in the 3rd decimal place. So right here it's a 4, whereas right there it's a 1.8. This is a 4.1. So yeah, the relativistic momentum is the right one, but in this case, it's not a huge percent. And this, by the way, is about the speed that that electron was going in the last lab. Remember, I told you this is the way old TVs were made, when they had old cathode ray tubes that you used for your TV because they would shot electrons at the back. So this is a ballpark figure of roughly how fast the electrons in those tubes, which is the same as the one in the Helmholtz coils yesterday. It's about the same ballpark of what the speeds were. So you can see they're pushing the envelope of being relativistic, but not quite there. So that's the momentum, and that gives us an explanation why the speed of light can't be obtained by anything with mass, because as the thing gets faster and faster, this momentum gets larger and larger and larger because of this factor depending on the velocity v. So you end up having to have an infinite force, or therefore an infinite amount of energy to get anything of mass greater than 0 up to the speed of light. Okay. Now the last thing I wanted to talk to you about is E equals mc squared. Well, I'll say the last two things because you sort of need one with the other. It turned out that Einstein discovered kinetic energy was wrong too. The kinetic energy that we're used to was equal to 1/2 mv squared. That didn't work. That didn't work with the laws of physics when he came up with the special relativity. He was able to fix it though by saying that kinetic energy turned out to be equal to gamma minus 1 times mc squared. Notice that's the speed of light. It has nothing to do with v. The only v comes in here. Surprisingly, if you take small enough velocities, you can use that that binomial expansion I showed you earlier, and you can show that this is really actually equal to 1/2 mv squared plus some other correction terms. And that's sort of the fundamental rule with science. If we find something that works in science and it works for decades or whatever, or for a lot of different problems, and then we find a new theory or hypothesis that we think is better, that new hypothesis better in fact correspond with the old hypothesis, at least in the realm where the old hypothesis was right. Bohr came up with that, and it's called the correspondence principle. So that's kinetic energy. Turns out this little mc squared is the rest energy, and that's where Einstein came up with E equals mc squared. So this is a new formula. You'll see some problems like it in the homework and stuff, but this E equals mc squared is really big. It's a really big deal. Let me give you a for instance. So for instance, if you wish to, let's consider making up the alpha particle. So the alpha particle is technically just a helium nucleus. It's not a big deal, but it was the first small particle that they discovered. It turned out to be the most massive. So, being really creative like physicists are, when they first discovered a particle, they named that one alpha. Then they discovered another one, they named that beta, and then they discovered a third, and they named that gamma. So the alpha was the first one. The beta turned out to be an actual electron, or actually, it might have been an anti-electron. And then the gamma turned out to be a photon. So this is stuck. But the big deal is the alpha particle is basically a proton and a neutron and a proton and a neutron. It's basically 2 protons and 2 neutrons. I made little pluses and N's in there. It doesn't really matter too much. I'm just telling you that it's 2 protons and 2 neutrons stuck together. Well, the mass of the neutron is actually a little bit bigger than the mass of the proton. It's 1.00, hopefully I'll remember this unit from earlier, 1.00866 atomic mass units. Okay. Now this atomic mass unit, if you ever forget it, it's basically just 1 over Avogadro's number. Okay, so if you take Avogadro's number, do 1 divided by it, that'll give you the conversion back to kilograms. The mass of the proton, on the other hand, was 1.00728 units. Okay, so in principle, you think the mass of the alpha particle would equal 2 times the mass of the neutron, 1.00866 U, plus 2 times the mass of the proton, 1.700728 U. And when you do that math, you come up with, I don't think I calculated that earlier, did I? No, I did not. Well, I did, but not on this paper anyways. So I'll do 2 times 1.00866 plus 2 times 1.00728, and I get 4.031 atomic mass units. Now, if you actually go up and look, so I'm going to put quotation marks around this because this is what I pretended. I know you don't see it yet. Hold on. I put quotation marks around this because this is not technically the right answer, as you'll see in a second. But in principle, in everyday life, we would think, based on Lavoisier, whoever his name was, the Frenchman who discovered conservation of mass, you would expect this to be exactly the right answer. But it turns out the actual mass of the alpha particle is 4.00153. Okay, so in other words, when you add up the parts of the alpha particle, you get a mass that's bigger than the actual mass of the alpha particle. So when we actually measured the mass of the alpha particle, we got this number. So that stood to reason, what the poop is this number? Well, it turns out, check this out. If you do 4.03188 minus 4.00, did I add extra zero somewhere? I think that's right. Double check my mass of my proton, my alpha particle. 4.00153. These are both in atomic mass units. So I'm going to say minus 4.00153 gives me 0.03035 atomic mass units. Okay. Now, that's the difference in mass. Now, according to E equals mc squared, we should be able to get an energy out of that. Well, U, as I told you before, is really just 1 over Avogadro's number. Well, if you take 1 and divide it by Avogadro's number, you'll get 1.66054 times 10 to the negative 27th kilograms. But if you take that kilogram and you multiply it by c squared, and then, of course, it'll turn out to be a number that's 1,000,000 times bigger than 10 to the negative 19th. So you can actually make this equal to 931.494 mega electron volts per c squared. So that's another unit of mass. You take energy and divide it by c squared, and that's a unit of mass. So that's what I was talking about earlier when I was talking about using the momentum in terms of energy per c. So they do everything in terms of energy and then put the c in the bottom or the c squared in the bottom or whatever like that. So the units all work out really nicely. So now if you use this as a conversion factor, 1 atomic mass unit is 931.494 MeV per c squared, then we can see the change in mass of the alpha particle would actually be 0.03035. Now I know what this answer is going to be. So if I was wrong about this decimal place, which kind of creeps me out and thinking maybe I was supposed to be over there, then it'll come out in this, because I know the answer is supposed to be about 28.3 mega electron volts. So what I'm going to do is multiply this by 931.494 MeV per c squared over 1U. So if I multiply that number times 931.494, actually wrote that backwards, 494. Nope, I was right. So it's 28.2708 MeV per c squared. So what that means is basically you don't have to think, by using these units, you don't have to think about how much energy it's going to become. It's already in terms of energy. If you want to know the energy, you're just going to multiply that mass times c squared. Well, it's the mass unit is in energy per c squared already, so you're just canceling out the c squared. So what this tells you is evidently the binding energy of the alpha particle is 28.3 roughly mega electron volts. So the reason that the alpha particle weighs less than the sum of its parts is, in fact, there's a loss in mass due to the binding energy. So that the whole reason I'm telling you this at all is, one, E equals mc squared is really important from a historical standpoint because it gave us nuclear power, nuclear weapons. And in fact, we learned that the energy, for instance, to break an electron off of a hydrogen atom, which is, you know, quite a bit better than the energy to break off a carbon atom, is 13.6 electron volts. Well, to break off a single particle from the alpha particle, that's literally 2 million times stronger. So that was the big deal, that going from molecular power to atomic power, we increased our energy by a factor of 2 million. So it's a really, 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 really big deal. Now, the other thing is this equation always, always, always applies. So, you know, if you look at the experiments of Priestley and Lavoisier, that's it, Lavoisier. If you look at his experiments where basically he did chemical reactions and he weighed all the stuff that went in, weighed all the stuff that came out, and he always found that they were exactly equal to within, you know, like I think he found like 10 to the negative fourth, in other words, you know, 4 or 5 decimal places. Well, if you actually did that with 100% precision, in other words, you can measure to any number of decimal places, you'd in fact find that the masses did not add up. In fact, whatever energy was created, like if you mix 2 chemicals and they get hot, obviously the fact that they got hot means that they created energy or created heat. And that energy you'd have to measure. And if you measured that energy and then you did the mass before and the mass after, you'd find that the mass after was really a little bit lower. But if you multiply that mass after, well, if you take the mass before minus the mass after, multiply that by c squared, you lo and behold get exactly the amount of energy E that made it warmer. So mass is not really conserved at all. And in fact, E equals mc squared happens every time energy is made. So when you burn a tank of gas, you put in X number of kilograms of gas and you put out X number of kilograms of, you know, soot and things like that, CO2, carbon monoxide as well, all those chemicals that come out. If you added up all those weights of everything that came out of your tailpipe and you know, collected on the inside of your engine and all that stuff, and then you subtracted out that from the original energy or the original kilograms of gas, you would find they don't match. But you would find they do match in exactly the sense that if you took that difference and multiplied it by c squared, you would get exactly the amount of energy that was created for your engine. So that's it. That's the big deal regarding relativity. That's all you really need to know about relativity. We could talk about Lorentz times Lorentz frames and stuff like that. We could also talk about how velocities add, which is a whole different story. I'm going to write it here just because it's an interesting formula. But normally we say the velocity of an object A with respect to the Earth is equal to, say, the velocity of object A. So this is like A would be me throwing the ball, E would be the Earth. The velocity of the ball with respect to the truck plus the velocity of the truck with respect to the Earth, that would be how we normally add those, right? If I threw a ball at 60 miles per hour in the same direction so that they both are positive, and the truck was going 60 miles per hour, then the sum would be 60 plus 70 would be 130. But in relativity, it turns out that's not exactly right. It's actually equal to 1 plus VAT, VTE over c squared. The main thing is these middle ones have to match, these outer ones have to match these over here, and then the formula always works. But that's how velocities add in relativity. So you'll find out if you add something that's, say, 3/4 c and let's say 5/8 c, if you just add it this way, 3/4 plus 5/8 would be 3/6 plus 5/8 would be 11/8. So you'd expect the thing to be going faster than the speed of light by 1/8 of the speed of light. But lo and behold, when you put it in here, it turns out that this formula gives you exactly the speed of light. So oddly enough, if you're traveling at 1/8 of the speed of light, or excuse me, 5/8 of the speed of light, and you shoot a photon beam, or let's say you shoot a fire a shell at us at 3/4 of the speed of light, in fact, the total velocity, since it's not light, will be a little bit less than the speed of light. Whereas if you put in, C and C, you're always still going to get C. So this is the last thing from the chapter. I don't get my students to do that, but if you want to play around with it a little bit, it's a neat little formula. You'll see in the homework you'll have opportunity to use mv squared and gamma minus 1 times mc squared. But both of those are not what I'll be testing you on. I test you up through momentum, which was 26.7. So the homeworks will be there. Some of them I make extra credit, some of them I make full credit. But the test will only be on 26.1 through 26.7. Any questions on that? All right, well, it looks like we're going pretty well on this. So what I'm going to do is I have a student asked about access for mastering, and I had another student ask about some stuff regarding lab, and another one asked about some stuff regarding mastering physics doing vectors. I'm going to use this time, everybody that's not wanting those questions answered, y'all can go ahead and take a break. Let's say we meet at 10 afternoon. Of course, it'll be a different Zoom meeting, but I'll open that one up at 10 afternoon but right now I'm going to try to address those questions. So everybody else is free to go if they'd like. So first off, we had that question regarding mastering. So let me pull up that. I think I can do here. That'll be fine. Share that screen. I'm going to go over here to this. I'm going to my lab and mastering. This is a pain in the butt because I think it might change windows. If it does, and y'all aren't seeing this, somebody please let me know that that it's changed. So I'm going to open my lab and mastering. So I suspect we're dealing with homework 24. Say all assignments. So when you look at this either in calendar form or in this list form, these will always be the right dates. So like I put 23 back here because we had done 23. We didn't really finish it until the Fridays, or excuse me, the Monday. So that's why I pushed it back. But let's look at 24 homework because I think that's where she had the vector problems. Good. It doesn't look like it's opening up in a new day, a new window. So that would be a pain when it does that. So let me look, student view.
I think it was 23 part 1.
Oh, you think it's 23 part 1? Thank you.
Yes, because I haven't even opened 24 yet. Oops.
Gotcha. It did open this. By the way, did y'all see this new window that just popped up, or is that something that you don't get to see now? It says chapter 24, 727. Do y'all see that right now?
No.
Crap. Yep, I knew that was going to be a problem. That's okay. We can switch when I get there. So I'm going to go back to all assignments, and you think it was 23 part 1. Because 424 was the chapter on that, but so well. So 23 part 2, that's 23 part 1. So that didn't open. So what I'm going to do, because y'all are not seeing this now, I'm going to do stop screen share, and now I'm going to do share screen again and see if I can see that new one that just opened. There it is. Okay, now y'all see that one. Good. All right, so ray tracing. I assume that's the one, right? Or these two. Lightning fast. So it tells you over here, an object O is placed at the location shown in front of a convex spherical mirror. Use ray tracing to determine the location and size of the image in the mirror. As you work, keep in mind the following properties of principal rays. So it's even telling you how to do the principal rays, if you will. So I'm going to go down here, and I think you can grab this and just start stretching it. See if I can stretch this window a little bigger for. So what we do is we know that a ray going through the focal point, first off, a ray parallel to the axis after reflection passes through the focal point F. So this one doesn't seem to be letting me change. See that? So I think I'm forced in this case to actually, and I'm just using the left mouse button, to actually lock this to the focal point. Okay, a ray through or proceeding toward the focal point is reflected parallel to the axis. So now I'm going to add another ray. So I hit that plus right there. And I'm going to say right here where it said, and now I'm going to stretch it horizontally this way. Evidently, the angle 180 corresponds to the angle that I wish. Okay, in other words, that's horizontal. So I'll put that there. So now what I've got is a this ray, which was a incident focal ray, and then this is the reflected focal ray. Now a ray parallel to the axis, so I'm going to draw another reflected. No, I don't want that. I want to add another. I didn't want that. Press enter to select the element, press tab or use arrow keys to move to the next element. Press escape to return to menu. Okay, so now I can take this ray. This is just an unlabeled vector. I'm going to try to make a ray that is parallel to the principal axis. And the angle I'm going to say is 0 this time, not 1. So I can just do like that. Now I can take a reflected ray the existing vector with this label will become unlabeled if you proceed. I don't care if it's unlabeled. Okay, so now I'm going to do a reflected ray. I'm going to add one. Why does it keep doing that? And didn't make a dot anywhere. So the dots evidently come up when the new vector is here. So this one, this ray is going to be reflected as if it came straight from here. So it's going to go up that way. And I think you can start to tell where the rays will converge. So let's do another unlabeled vector, I guess. I'm going to drag this right to that spot. And now I can see that this ray and this ray are going to converge back here. So I just need to draw another vector back here. So I'll say unlabeled vector. I'm going to put it from here. Stretch it back this way at 0 degrees. Don't worry too much about getting exactly 0 because you can just do this, click on it, and then Tap that to 360 and that'll make it horizontal. So now we know where the object is. What it wants us to do is, as you work, keep in mind, okay, I did ray through, proceeding to ray along the radius. The focal length's not actually shown over, yeah, it can't be here. Let's be like that. Array along the radius through A. I guess I could probably hit right here. Yeah, and that would actually be the front center, so it's going to bounce off horizontally. I mean, the angle of incidence is going to equal the angle of reflection. So I could add another label if I wanted, another ray if I wanted, and just say it's going to start here. Now in this case, it should come back off at exactly the same angle. So whatever this angle was 323. I want this one to be a 100 and, or excuse me, let me see what angle this is. 323 would be that way. So 323 is this. This would be 270. This angle would be 323 minus 270 would be 63. So I want this to be 63 beyond 180. So that'd be 243. It can't be right. Okay, that angle right there is 323. 360 minus 323 would be 37. So that means this angle is 37. So this angle should also be 37. So it's 180 plus 37. That'd be 217. That sounds more right. Okay, and then that angle, or that ray, of course, would continue back here. So I'll do right here. Again, not perfectly on it, but not horribly. So I'm thinking the actual object will be right there. Now, so do you understand how to draw the actual vectors now? Whoever it was that asked this, I'm sorry.
Yeah, it's still really confusing, but yeah, I guess. Well, can you submit it and see if that's
That can't be right, because right now I know I have to label all this, and I have to, it does it even tell me? Oh, here it is. Trace the path of a ray emitted from the tip of the object toward the focal point of the mirror, and then, oh, okay. Duh, this was part A. I didn't see this instruction at all. This would have been a lot more helpful because I was trying to do them all. So trace the path of a ray emitted from the tip of the object toward the focal point of the mirror, and then the reflected ray that results. Start by extending the existing ray emitted from the tip of the object, then create the reflected ray. Okay, so what I was supposed to do was do what was done here, so I'll kill this. I'll go ahead and get rid of all these. Since those, I didn't read the instructions, I was doing a bunch of stuff that wasn't necessary. Let's go back. Okay, so what I'm supposed to do with this guy is take it all the way to here. And that's not exactly perfect, but it's evidently good enough. And it says, start by extending the existing ray emitted to the tip of the object, from the tip of the object, then create the reflected ray. So now the reflected ray, I'm going to add that, and that's why it wouldn't give me more. So I'm going to start, and even CNO giving us a hint. When it first came on, the dot was right here. Now this is where I'm going to make this exactly 180. Let's check and make sure I did. I did do 180. So this should be the submit part. So that one was correct. Does that make sense?
Yeah, thank
What
you.
it did, it was expecting you to do, I was trying to do all of them because I didn't read this top part, but it's expecting you to do one part at a time.
Okay.
You know what this one's going to make you do? Notice it's parallel to the axis. So this is the one that says, now trace the ray, path of the ray emitted from the tip of the object parallel to the axis of the mirror, and then the reflected ray that results. So do you know where that would reflect?
Would it go like straight across, or would it go to the focal point?
Yeah, it goes to the focal point. Exactly. So it's going to go to the focal point, but it also, because this is a mirror surface, it's actually going to reflect back along that line this way.
Okay, so that's where the second one would go.
Exactly.
Okay.
We'll try it again just to make sure we're right. So I want this one to be at 0 degrees. Let's see what it is. I click on the object. It says the angle is 359. That's not what I want. I thought it would give me a box that would actually allow me to make it 360. And it's kind of being a jerk because it's not allowing me to do 360. It's pushing me down. But we'll see if it actually allows us to do it correctly. So it now says, now trace the path of a ray emitted from the tip of the object parallel to the axis of the mirror, and then the reflected ray that results. Start by extending the existing ray emitted from the tip of the object, then create the reflected ray. So the reflected ray, I'm going to add that. I'm going to start it here. And I'll lift it right across here. See if I can now change the angle of this sucker, because it was not exactly right. Damn it, why won't it let me change it? It's being a jerk. Okay, so that should be fine. Now let's submit and see what happens. I'm hoping it's within error. Nope, it's not within error. Why is it not doing this? Anybody able to get this one? Anybody that's around here now? I wonder if it's actually trying to make me just do this part. Ah, that's what it was. Okay, so what you're going to do in this case is you're going to draw from here through that and then read the angle that it gives you. And then just shorten it and make sure it still reads that same angle and still hits right here. And then you'll get it correct. Does that make sense?
Yeah.
Okay, so now you can look at that and you look at this and you can see based on this, the only place these two rays are going to converge, this one, which goes back to here, which is like this, and this one that goes back to here, they're going to have to converge on this side. You can see it's upright. So right here, the image, the virtual image behind the mirror, submit that.
So if we wanted to go back and do these, because I know I skipped them all because I was very confused, but would it be like 10% off, or would you be willing to reopen?
Yeah, I think I said it where you get partial credit for late submission. So
Okay.
you should, if it seems to not do that, just let me know and I'll go back in and add the points manually.
Okay.
Would we be able to
Okay.
get a second attempt on this homework? Because I would do this and put the answers in and they looked the exact same, but it would say it was wrong.
Yeah, okay, let me see what I can do with this then. I'm gonna stop this share. Let's see. Hold on a second, let me look at what my controls have on my side. And kill that. Okay. Okay, so what I did, everybody, those of you that are still here, is it allowed me to set up the grading such that, and I couldn't find this earlier, so that's why I hadn't done it before. It allowed me to, yeah, I just changed that and it didn't change. So maybe it didn't work. Yeah, I just changed this and it didn't say, let's say, I allowed it to be where basically each day you're late, it's going to get 5% off. But I'm never going to let you go below 25%. So that'll give you an impetus to do it even if you are really, really late. So I've got this. And okay, it says my changes are saved, but it said that last time. Let me check and see if it's still there. Okay, it's working now. So yeah, now you can do that. There's no way I can get it to do a second trial because that's not a randomized problem. Let me see if it'll let me. Okay, yeah, I can do that, I think. Okay, so I also allowed you to do it up to 3 times.
Thank you.
No problem. And I think I'm going to make that the default setting from now on. Now that I found it, I've been looking for that literally for 3 years, but I had to go a different way. So that's why I found it this time, I guess. All right, so we addressed that question. The other question I had was a student trying to find an access code. Do you mean, well, actually the student might not even be here. I'll talk about that again later. There was something regarding, oh yeah, I think I already answered that one about the lab that we're getting ready to do. So it's about 12:13 now. I'm going to end this one, everybody, and go over to the other one.